From a distance, galaxies seem like simple islands of stars, glittering clusters scattered through a dark and silent sea. But this is an illusion of scale. A galaxy is not merely a collection of stars. It is a vast, self-governing ecosystem, held together by gravity and shaped by thousands of subtle forces. Within it flow rivers of gas, storms of radiation, collapsing clouds where new suns are born, and ancient remnants of stars long dead. Every galaxy is a city on a cosmic scale, structured, dynamic, alive. Yet the universe did not begin with these luminous cities. In the earliest moments after the Big Bang, there were no stars, no planets, not even the faintest traces of light. Only darkness, expanding space, and thin clouds of hydrogen and helium drifting in a no-perfect silence. The first seeds of galaxies were nothing more than tiny fluctuations in density, small wrinkles in the fabric of space-time. Gravity amplified these wrinkles, pulling matter closer, letting the first clumps take shape. What began as chaos slowly folded into structure. Today, the observable universe contains trillions of galaxies. Spiral giants with sweeping arms, compact ellipticals glowing like cosmic embers, and irregular forms twisted by collisions and ancient violence. Despite their incredible variety, all of them share one origin: the simple gravitational gathering of matter in the young universe. It is a story of order emerging from disorder, of darkness giving birth to the first sparks of light. As we trace this journey, from the silent cosmic fog to the grand star cities we see today, we uncover not just how galaxies formed, but how structure itself rises from chaos. It is a quiet, poetic reminder that even the universe began in shadow and learned, over billions of years, how to shine. In the first few 100,000 years after the Big Bang, the universe was a warm, glowing fog, dense, uniform, and almost perfectly smooth. Almost. Embedded within this cosmic haze were slight imperfections, tiny fluctuations in density only millionths of a percent stronger or weaker than their surroundings. We can still see the imprint of these ancient ripples today in the cosmic microwave background, a faint afterglow that preserves the earliest map of the universe. These peaks and valleys in density were the first hints of structure, the faint blueprint from which all galaxies would one day arise. But ordinary matter alone could not have formed galaxies. It interacted with light, moved too easily, and lacked the gravitational strength to collapse fast enough. The true architect in these early times was dark matter, an invisible substance that does not emit or absorb light but responds powerfully to gravity. While normal matter was still coupled to radiation, dark matter began collapsing freely, gathering into enormous, invisible halos. These halos acted like scaffolding, deepening the gravitational wells created by the initial fluctuations. As the universe cooled and atoms finally formed, gas was able to drift into these dark matter wells. Hydrogen and helium began to pool in the invisible valleys carved out by dark matter, falling inward like mist settling into a landscape of unseen mountains. Every future galaxy was seated in one of these gravitational depressions. Without dark matter, the early universe would have remained too smooth, too diffuse, too evenly lit for stars or galaxies to ever assemble. It is the silent framework, the hidden skeleton of cosmic structure. What began as tiny quantum fluctuations grew into vast gravitational basins, pulling in matter over hundreds of millions of years. These basins are where galaxies took their first breath, where darkness gathered the material that would one day ignite into trillions of stars. As the early universe continued to cool, the vast reservoirs of hydrogen and helium that filled space began to behave differently. No longer held back by the intense radiation of the young cosmos, these primordial gases drifted freely into the deepening gravitational wells carved out by dark matter. What formed were enormous, sprawling clouds, structures so large that they dwarfed anything that would ever appear again. These were the first galactic nurseries, the raw material from which every future galaxy would rise. Inside these gigantic clouds, cooling became the dominant force. As the gas radiated away energy, it slowly contracted, becoming denser and more structured. But this collapse was anything but smooth. Turbulence churned through the gas like storms in a cosmic ocean. Shock waves rippled across thousands of light years, stirring the mixture of elements, creating knots of high density and pockets of relative emptiness. Gravity fought with chaotic motion, shaping the clouds into complex, layered regions. Over time, the gas naturally separated into zones of different densities. Some areas thinned out, expanding like gentle cosmic breezes. Others grew heavy and thick, collapsing into compact regions that would eventually give birth to the first stars. These dense pockets formed the earliest protogalactic structures, clumps of matter that were not yet galaxies but carried the unmistakable blueprint of what galaxies would become. They were uneven, fragmented, and wild, reflecting the unruly nature of the young universe. The early cosmos was far from calm. It pulsed with turbulence, with rapid flows of gas, with chaotic mixing driven by gravity and pressure. Yet out of this chaos emerged order. The massive gas clouds, shaped by both instability and attraction, were the fertile grounds where galaxies began their long journey toward structure and brilliance. What looked like disorder was, in truth, the first stage of cosmic architecture. As the earliest protogalactic clouds continued to collapse, the universe approached a turning point, its first dawn. For hundreds of millions of years after the Big Bang, space was dark. No stars existed, no galaxies shone, and the cosmos was a silent ocean of cooling gas. But as gravity tightened its grip on the densest pockets of hydrogen and helium, these regions grew hotter and denser, pushed inward by their own weight. Eventually, conditions became extreme enough for something entirely new to ignite: the first stars. These primordial stars, known as population 3 stars, were unlike anything we see today. Made from pure hydrogen and helium, the only elements forged in the Big Bang, they formed with almost no cooling mechanisms. Without heavier elements to help shed heat, the gas collapsed into enormous clumps. As a result, population 3 stars were gigantic, often hundreds of times the mass of the Sun. Their surfaces blazed with temperatures far hotter than modern stars, and their ultraviolet radiation flooded the young universe with light for the very first time. But their brilliance came at a cost. Massive stars burned through their fuel with incredible speed, and these cosmic giants were no exception. Their lifetimes were astonishingly short, lasting only a few million years, a moment compared to the cosmic timeline. When they died, they did not fade gently. Many ended in titanic explosions, violently dispersing the first batches of heavy elements, carbon, oxygen, silicon, iron, into space. Others may have collapsed directly into black holes, leaving behind invisible gravitational anchors that would later shape new structures. These explosions fundamentally changed the universe. The heavy elements created in the hearts of the first stars mixed with the surrounding gas clouds, enriching them with the materials needed for planets, complex chemistry, and eventually life. This process, known as metal enrichment or metallization, transformed the character of cosmic gas. What had once been a simple mixture of hydrogen and helium became a more diverse, chemically rich medium. With metals now present, the gas could cool more efficiently, breaking up into smaller fragments. This allowed the birth of the first normal stars, population 2 and later population 1, smaller, more stable, and longer lived than their gigantic predecessors. These generations would build the galaxies we know today, turning the universe from a dark expanse into a cosmos filled with light and complexity. The formation of the first stars marked the end of cosmic darkness and the beginning of cosmic history as we recognize it. Their brief, fierce lives lit the path for everything that followed. As the universe emerged from its first generation of stars, another transformation quietly began, one that would determine the architecture of every future galaxy. Not all population 3 stars ended their lives in explosions. The most massive of them, far exceeding dozens or even hundreds of solar masses, collapsed directly under their own gravity. Their cores imploded so violently that no supernova could escape. Instead, they formed the first black holes in cosmic history. These primordial black holes were small by today's standards, perhaps only tens or hundreds of solar masses, but they were born into an environment rich with gas and turbulent motion. Surrounded by dense protogalactic clouds, they found themselves in the ideal setting to grow. As matter spiraled toward them, it formed blazing accretion disks, heating to millions of degrees and radiating intense energy. In a young universe still saturated with raw material, feeding was easy. Over millions of years, these early black holes continued to swallow gas, dust, and even nearby stars. What began as tiny gravitational seeds gradually grew into giants. We believe these early objects formed the seeds of the supermassive black holes that today sit at the centers of most galaxies, including the one at the center of the Milky Way. Their growth wasn't quiet. As gas fell inward, the energy released powered some of the first quasars, blindingly bright beacons that outshone entire galaxies. These early quasars acted as cosmic engines, heating surrounding gas, shaping star formation, and influencing the development of young galaxies. They regulated the very growth of the structures forming around them. In this way, the earliest black holes became the gravitational hearts of future galaxies. What began as collapsed remnants of the first stars evolved into anchors around which entire stellar cities would rotate. Their presence shaped the cosmic landscape long before galaxies settled into the familiar spirals and ellipses we see today. As the young universe expanded and cooled, its earliest protogalaxies did not grow in isolation. Instead, they existed in a restless cosmic web, an interconnected network of dark matter filaments guiding the flow of gas and stars. Along these invisible highways, small protogalactic clouds drifted toward one another, drawn by gravity into an inevitable sequence of encounters and collisions. These mergers were not gentle. When two protogalaxies approached, their stars rarely collided directly. Space is too vast for that. But their gas clouds, dark matter halos, and gravitational fields interacted violently. Gas compressed, shock waves spread through the merging systems, and bursts of intense star formation ignited like cosmic fireworks. Young, massive stars formed in clusters, shining blue-hot before ending their lives in spectacular supernovae. As these early systems merged, they twisted into bizarre, chaotic shapes. Long tidal tails of stars stretched across space, like luminous ribbons pulled away by gravitational tension. Streams of disrupted material wrapped around the merging galaxies, creating arcs, loops, and wandering currents of ancient stars. These structures, visible even in nearby interacting galaxies today, are the fossil signatures of cosmic construction work. From countless small mergers emerged the first substantial galactic bodies. Repeated collisions between fluffy, irregular protogalaxies gradually formed the massive structures we recognize today. Some settled into rotating disks, eventually becoming spiral galaxies with graceful arms curling outward. Others, born from more violent and frequent mergers, became large elliptical galaxies, smooth, round, and filled with older stars. This process, hierarchical assembly, was the blueprint of cosmic evolution. Everything from the elegant spirals to the massive ellipticals began as fragments stitched together over billions of years. By studying these ancient collisions, we uncover the story of how galaxies grew from modest beginnings into vast stellar metropolises, shaped at every stage by gravity's relentless hand. As the turbulent stage of mergers gradually subsided, a new kind of structure began to emerge within young galaxies, a fragile but profound step toward order. After the violence of early cosmic collisions, much of the remaining gas still moved chaotically, swirling in thick, uneven streams. But gas, unlike stars or dark matter, can lose energy. It radiates heat into space, cools, and slowly settles. As this cooling gas continued to orbit the galaxy's growing gravitational center, the most energetic, vertical motions dissipated first. What remained was motion dominated by rotation. Bit by bit, the gas collapsed into a flattened, rotating disk, a natural outcome of angular momentum conservation. Instead of drifting freely in all directions, gas clouds began to follow stable, circular paths. This was the birth of structure, of geometry, of order inside a once chaotic protogalactic cloud. Colder gas had an even greater advantage. It could settle into the disk more efficiently. Lower temperatures meant less internal pressure pushing outward, allowing gravity to shape the gas into a thin, elegant plane. Within this disk, dense regions formed spiral patterns, waves of compression that shepherded gas into long, curving arms. These arms became the primary sites of star formation. Massive blue stars ignited along them, marking the first organized stellar architecture of the young galaxy. The transformation from chaos into a coherent disk was one of the most important evolutionary milestones in galactic history. Without this process, spiral galaxies, those grand, sweeping structures we admire in astrophotography, would never exist. Our own Milky Way followed this path. After countless early mergers, the remaining gas gradually cooled and settled into a rotating disk. Over billions of years, this disk became home to new generations of stars, including the Sun. The galactic disk is not just a structural feature, it is a living environment where stars are born, evolve, and eventually enrich the galaxy with new elements. From turbulence to symmetry, from collisions to order, the formation of the disk was the moment when galaxies began to resemble the cosmic cities we know today. One of the most persistent misconceptions about spiral galaxies is the idea that their spiral arms are rigid structures, vast cosmic highways along which stars travel in graceful curves. But this picture is deeply misleading. Spiral arms are not physical objects. They are not permanent arrangements of stars locked into fixed positions. Instead, they are patterns, waves of density, moving through the galactic disk. To understand this, imagine a traffic jam on a highway. Cars enter the jam, slow down while passing through it, and then speed up again as they leave. The traffic jam itself, its location, can persist even though the cars constantly change. Spiral arms work the same way. They are regions where the density of gas and stars is temporarily higher, creating a wave pattern that slowly rotates around the galaxy. Stars inside a spiral galaxy orbit the center at different speeds depending on their distance. They do not remain embedded in the arms. Instead, they pass through them. When a star or a cloud of gas enters a spiral arm, the gravitational compression in that region slows it slightly, just enough to enhance the density contrast. Gas clouds that encounter this compression are squeezed, increasing their internal density until they collapse to form new stars. That is why spiral arms appear so bright. They are stellar nurseries. The massive, short-lived blue stars that are born there illuminate the arms with intense radiation. These stars live only a few million years, far too short to leave the arms before they explode as supernovae. Meanwhile, smaller, longer-lived stars eventually drift away, spreading throughout the galactic disk. The arms themselves rotate at a different speed from the stars and gas, maintaining their shape over long periods even as individual stars continuously move in and out. This density wave theory is one of the most elegant explanations in galactic dynamics. It transforms the spiral pattern from a literal structure into a dynamic process, an ever-moving wave sculpting the disk from within. In this sense, a spiral galaxy is not defined by static architecture but by rhythm. Its arms are not fixed pathways but passing waves, marking the regions where gravity, gas, and motion briefly synchronize to bring new stars into existence. When we look across the observable universe, we see galaxies arranged in a remarkable diversity of shapes, graceful spirals, massive featureless ellipses, and chaotic irregular systems that refuse to fit into any neat category. This variety is not decorative. It is the fossil record of each galaxy's life story, shaped by environment, gas content, and its history of interactions. The most familiar type is the spiral galaxy, such as our Milky Way. Its appearance is defined by a rotating disk filled with cold hydrogen gas. Cold gas is essential because it can collapse under gravity and form new stars. This ongoing star formation illuminates the spiral arms with bright, young, blue stars. A stable disk and abundant cool gas produce the ordered, elegant structure that makes spirals some of the most visually recognizable galaxies in the cosmos. In contrast, elliptical galaxies are far more massive, smoother, and redder. They have little or no cold gas. Without gas, there is no new star formation. Their stars are old, metal-rich, and move in random orbits, creating a rounded, featureless appearance. But how does a galaxy become elliptical? The most common mechanism is major mergers, collisions between galaxies of comparable mass. These violent interactions scramble stellar orbits, heat the gas, and often remove or exhaust it entirely. The result is a large, smooth, dynamically hot system dominated by old stars. Ellipticals often inhabit dense environments like galaxy clusters, where mergers and interactions occur frequently. Then we have irregular galaxies, systems that appear distorted, fragmented, or asymmetrical. Many irregulars started as small spirals whose structure was disrupted by a close encounter with a larger neighbor. Gravitational tides can tear a galaxy apart, removing its disk, twisting its gas into knots and streams, and pulling stars into chaotic distributions. Some irregular galaxies are simply too low in mass to form stable disks in the first place. With shallow gravitational wells, even mild interactions or bursts of star formation can reshape them dramatically. Environment plays an enormous role in determining a galaxy's fate. A small galaxy falling toward a massive cluster may be stripped of its gas by hot intracluster plasma, a process known as ram pressure stripping. Without gas, it can no longer sustain star formation, slowly transforming into a red, quiescent system. Conversely, an isolated galaxy with abundant cold gas can maintain its spiral structure for billions of years, relatively undisturbed. The morphology of a galaxy, then, is not an accident. It is a physical consequence of its surroundings, its mergers, its gas content, and the gravitational forces it has endured. Every shape, spiral, elliptical, or irregular, is a signature written into its stars, encoding billions of years of cosmic evolution. Galaxies are not static islands of stars. They evolve, age, and change their character over billions of years, gradually transforming from energetic, star-forming systems into quiet, reddish structures that have exhausted their internal fuel. In the early universe, young galaxies are vibrant, chaotic, and intensely blue. Their color comes from massive, short-lived stars that burn hot and bright, illuminating the surrounding gas. These galaxies contain large reservoirs of cold hydrogen, and the high density of gas clouds triggers rapid bursts of star formation. Young galaxies often collide and merge, feeding their central black holes and shaping their eventual morphology. Many early galaxies host spectacular quasars, supermassive black holes consuming gas at such extreme rates that the galaxy's core can outshine the entire galaxy around it. As time passes, galaxies use up or lose much of their cold gas. Interactions, supernovae, and energetic outflows from active galactic nuclei gradually heat or expel the material needed to form new stars. When the gas supply dwindles, the galaxy's color shifts. The bright blue light of young stars fades, leaving behind older, cooler, redder stars that dominate the visible spectrum. These aging galaxies appear calmer and more orderly, but in reality they are simply running out of the fuel required to maintain their youthful brightness. Eventually, many galaxies enter a phase of long-term quiescence. The once blazing quasar becomes a dormant black hole, no longer fed by fresh material. Star formation drops to nearly zero. The galaxy becomes a red and dead system, its stellar population aging slowly, its structure shaped more by gravitational evolution than by new creation. The life cycle of galaxies is therefore a story of fire, exhaustion, and transformation. From blue star factories in the early cosmos to red, quiet structures that drift through space, carrying the memory of their brilliant past. Galaxies, like stars, follow a long and irreversible evolutionary path. Over billions of years, they slowly exhaust the very resource that sustains their brilliance, cold gas. Without this raw material, star formation fades. The bright blue beacons of massive young stars disappear first, leaving behind only older, cooler, redder stars. As this transition unfolds, a galaxy that once blazed with stellar birth gradually dims, its luminous energy slipping into a quiet twilight. This process creates systems known as elliptical galaxies, vast, smooth, spheroidal structures sometimes called galactic steps. They lack spiral arms, lack cold gas, and lack the chaotic beauty of star-forming regions. Instead, their light comes almost entirely from ancient, long-lived stars. Their shape reflects a turbulent history of mergers, collisions, and gravitational reshaping. Ellipticals are the final resting places of galaxies that have run out of fuel, stabilizing into a silent equilibrium where almost nothing new can be born. The distant future of the Milky Way follows the same trajectory. After its eventual merger with the Andromeda Galaxy, the violent mixing of stars and gas will ignite a brief renaissance of star formation. But once that temporary burst ends, the combined system, often called Milkomeda, will slowly settle into the long red quiet of an elliptical galaxy. Over trillions of years, the stars will age, fade, and cool, until only faint embers remain in a structure that once held hundreds of billions of suns. In the far future, galaxies will not end with an explosion, but with a gradual fading of light, a slow descent into cosmic dusk. Their death is not destruction, but a quiet turning inward, as the universe grows older and darker around them. When we look at a galaxy, we are seeing the outcome of billions of years of cosmic struggle, chaos shaped by the quiet persistence of gravity and the long patience of time. What begins as faint ripples in the early universe eventually becomes a stable, luminous structure stretching across hundreds of thousands of light years. Galaxies are not accidental. They are the universe's most elaborate constructions, molded by physics yet carrying a kind of quiet elegance that feels almost intentional. Every galaxy contains billions of individual stories. Each star is a furnace where elements are forged, each nebula a nursery where new suns awaken, each supernova a moment of violent renewal. The motions of stars trace the invisible architecture of dark matter. Spiral arms mark the rhythmic passage of density waves. Central black holes sculpt their surroundings with the force of entire galaxies. What appears serene from afar is, in truth, an intricate ecosystem, dynamic, evolving, endlessly reshaped. And yet, beyond the scientific complexity, there is a deeper resonance. Galaxies embody the universe's ability to organize chaos into structure, and structure into beauty. They are reminders that order can emerge from turbulence and that the cosmos spends its entire existence learning how to build, refine, and illuminate. A poetic closing thought. When we look at a galaxy, we are witnessing the universe learning to create beauty, one luminous spiral, one drifting star, one quiet collision at a time.